In section 7.4, we'll pick up our third gas law, which defines the relationship between volume, pressure, and temperature of a gas. The best way to accomplish this is to define the mathematical relationship and work through some problems. Let's begin. Boyle's law and Charles' law can be merged into one law called the combined gas law. In calculations, 5 of the 6 parameters are provided. The key points to remember are that the pressure and volume units must agree, and all calculations rely on use of the absolute temperature in Kelvin. Let's work some examples. In our first problem, a 17.3 milliliter sample of argon gas was originally at 0 degrees Celsius and 1 atm pressure. If its final volume is 10.9 milliliters and its final pressure is 678 torr, what is its final temperature in degrees Celsius? First, we'll tabulate the data and make any needed conversions to get the volume and pressure units to match and all temperatures in Kelvin. Next, we'll rearrange the combined gas law, P1V1 over T1 equals P2V2 over T2, to solve for T2. T2 equals P2V2 T1 over P1 V1. Dropping in all the values, we get T2 equals 0.892 atm times 10.9 milliliters times 273 Kelvin divided by 1 atmosphere times 17.3 milliliters. Solving, we get T2 equals 153 Kelvin, or in degrees Celsius, T2 equals 153 Kelvin minus 273.15 equals negative 120 degrees Celsius. As always, I'd like you to ask yourself, does this result make sense? Since V and P both decrease, we should see T2 less than T1, which is the case. In this next question, I've organized the data, but I'm going to turn you loose on it to see if you can manage the individual steps. I'll ask questions, then we'll go over the answers to each piece together. First, convert the temperatures to the proper scale. We see 20 degrees Celsius needs 273.15 added to it to get 293 Kelvin. 72 degrees Celsius becomes 345 Kelvin. After we add 273.15 and round to 3 significant figures, the volumes can remain unchanged, but the units of pressure need to agree. Let's take P1 to atm by taking P1 equals 717 torr times 1 atm over 760 torr to give us 0.943 atm. Next, we need to rearrange the combined gas law to solve for V2. If we multiply both sides by the reciprocal of P2 over T2, we'll isolate V2. Dropping the data into the equation, we get V2 equals 0.943 atm times 908 milliliters times 345 Kelvin divided by the product of 293 Kelvin times 1.07 atm. This gives us a final answer of 943 milliliters. I'll leave you with the parting thoughts of the authors.